Hi, this is the basic principles of hemodialysis divided into two parts. In part 1, the principles of hemodialysis. Hemodialysis is a treatment which aims to, first, to remove accumulated metabolic waste products, to correct the blood electrolyte composition by means of an exchange between patient's blood and a dialysate fluid that happens through a semi-permeable dialysis membrane and in a flowway called a counter-current mechanism that will be discussed later. Also to remove excess fluids by means of ultrafiltration. The counter-current blood dialysate flow means that the dialysate is flowing in the opposite direction to the blood flow in the extracorporeal circuit. Countercurrent flow maintains the concentration gradient across the membrane at a maximum and increases the efficiency of the dialysis. The countercurrent approach is used for intermittent hemodialysis to provide the maximum diffusive gradients and the maximum removal of uremic toxins, as fresh dialysate fluid is continuously exposed to solute uremic toxins-laden blood. The countercurrent blood dialysate flow in depth, we can find that in the first part of blood entry, the dialysate fluid is already concentrated, but less so than the blood, thus there is still a concentration gradient. While in the middle, the concentration gradient remains the same. The blood is depleted of solute at the same rate as the dialysate is enriched by it. At the end of the blood circulation from the dialyzer, the concentration gradients remain the same. The solute depleted blood is exposed to a completely clean dialysate, and the concentration gradients remain unchanged. So the two fluid exchange solutes almost completely to remove solutes. This is more efficient way to do it, even though the driving force and the driving concentration gradient is never very high. So we have a blood pathway and a dialysate pathway and diffusion process all through the dialysis. The blood flow is called QP and the dialysate flow called QD, and both are in milli per minute. The blood compartment is separated from the dialysate compartment by a semi-permeable dialysis membrane. So QP is the blood flow inlet in milli per minute, and the QD is the dialysate flow inlet in milli per minute, while concentration of solute in blood inlet in milligram per deciliter, and the concentration of solids in blood outlet in milligram per deciliter. So there is a diffusion and the back diffusion separated by the semi-permeable membrane, where diffusion is movement from the blood compartment to the dialysate compartment, while back diffusion is movement from the dialysate compartment to the blood compartment. Diffusion is important in removal of toxins, as well as removal of other toxins like potassiums, while back diffusion is important in bicarbonate infusion, glucose, calcium, and others. So movement of molecules from the blood side is called clearance or diffusion, while movement of molecules from the dialysate side is called back diffusion. the semi-permeable membrane in hemodialysis. This allows certain molecules to pass in both directions, while it retains other molecules to pass from the blood side as well from the dialysate side. Important molecules, bigger molecules like albumin as well cells are not passed. So the basic principle of dialysis, principles related to solid removal like diffusion and convection, as well principle related to water removal, which is called ultrafiltration. The diffusion is defined as the spontaneous passive transport of solids from blood to dialysate and vice versa across the dialysis membrane through a concentration gradient. The rate of diffusive transport depends upon diffusion coefficient of solids, how much the solid is fast enough to move from the blood through the dialysis membrane and in the dialysate, the concentration difference across the membrane, and the surface area of the membrane. High diffusion coefficient of the solid, high concentration difference across the membrane, and bigger surface area of the dialyzer increase the rate of diffusive transport, while the transport rate of solid is inversely proportional to the molecular weight. So smaller solid can diffuse easier than bigger molecules. Solids removed against a concentration gradient in a random fashion. Small solids diffuse easier, large solids diffuse slower. In hemodialysis, there is a boundary layer around the dialysis membrane, and other makes some resistant to diffusion. Diffusion process is slower in bigger molecules, thicker dialysis membrane, low temperature, and low concentration gradient. Sometimes there is a specification of the dialyzers called mass transfer area coefficient and called KOA, expressed in milli per minute for a given solid, which is commonly described for KOA urea, which means the clearance of the dialyzer at infinity high blood and dialysate flow rate on a theoretical basis. Therefore, KOA is the measure of the maximum solid removal capacity of the dialyzer and has been considered as an intrinsic property of the dialyzer membrane. It's calculated from the clearance value, the blood flow QP, and the dialysate flow QD. KO is the diffusive permeability, while A refers to the surface area of the device. In mass transfer area coefficient, depends on molecular weight of solid, which is higher for urea, lower for other bigger molecules, membrane pore size, number, and distribution, membrane thickness. Thicker membrane will have lower KO value, diffusive resistance of the dialysis membrane, membrane surface area, bigger surface area has higher KO value. The second basic principle of solid removal is called convection. Convection is the simultaneous transport of solvent and solid, dissolved solid, from the blood compartment to the dialysate compartment. sometimes from the dialysate compartment to the blood compartment, and this is called back filtration and will be discussed later. Solid transfer across the semi-permeable membrane by pressure makes solid drag, and convection transport across the membrane has many determinants. Water flux across the membrane, more water flux, more dragging of the solids and more convection. Pore size of the membrane, bigger pore size, more molecule removal. Molecular size, bigger molecules, movement is less, as well sometimes in solid charges. So in convection therapy, we can find that very big molecules like albumin is not removed, while the middle molecules can be easily transported. So in convection, the movement of solids with fluid flow, while the solids are dissolved in the fluid, this phenomena can be observed during ultrafiltration. And this is the basic principle of hemodiafiltration as well, giving that the membrane is permeable for them, and the solids will follow the ultrafiltered fluid across the membrane. So, movement of fluids carries the dissolved solids, depending on ultrafiltration rate, transmembrane pressure, and more efficient in middle molecules removal. The convective process requires a fluid movement caused by a transmembrane pressure gradient. Solid flux depends on how much ultrafiltration rate, the solid concentration in plasma water, and the sieving coefficient of the solid through a pressure gradient. In adsorption, with increasing size of the middle-sized proteins and the other compounds, relatively more clearance is achieved by membrane adsorption compared with loss into the dialysate. A high absorptive capacity, one of the main features of some dialysis membrane like polymethyl methacrylate PMMA membrane, can absorb more low molecular weight protein than others. Important in removing protein-bound uremic toxins from the blood, and these protein-bound uremic toxins removal by means of diffusion or convection is virtually impracticable. However, protein-bound uremic toxin can be removed by using the adsorptive capacity and the properties of particular membranes, while PMMA membrane has higher adsorptive capacity more than in polysulfone. The adsorption happens early on start of hemodialysis, and the protein are adsorbed on the internal surface of the dialysis membrane, while moving of protein from the blood toward the membrane with time can induce clogging, and this protein clogging in the internal part of the membrane is called protein fouling. In the basic principles of water movement or ultrafiltration, the ultrafiltration rate is defined as the volumetric flow rate of solvent across the membrane per unit of time. In hemodialysis, Ultrafiltration is movement of water across the semi-permeable membrane because of a pressure gradient with positive pressure in hydrostatic as well osmotic or oncotic pressure of the plasma proteins play how much fluids can be removed. So in dialysis, the blood pressure within the hollow fiber is positive, while the pressure outside the hollow fiber is lower. The difference between the pressure inside the hollow fibers and the surrounding pressure in the dialysate side is called the transmembrane pressure. The transmembrane pressure determines the ultrafiltrate production. So exertion at pressure on one side of the membrane produces a filtration of water with solids as long as they can pass through the membrane. In the blood compartment of the dialyzer, a positive pressure is created when the blood is pumped into the narrow fibers. In the dialysis fluid compartment, there is usually a negative pressure. So fluid moves from the blood side to the dialysate side and is clearly obvious in low flux dialysis. The pressure gradient created is the transmembrane pressure. So while blood is moving, there is a transmembrane pressure which equals positive pressure in the blood side as well the negative pressure in the dialysate side. And you can find that the second part of the dialyzer has more protein and more hematocrit. So here is some concentration of the blood. With maximum ultrafiltration in the first part of the dialyzer and lower ultrafiltration in the second part of the dialyzer. So the transmembrane pressure and the membrane hydraulic permeability or ultrafiltration coefficient regulate the rate of the movement of fluid across the dialysis membrane, while KUF means ultrafiltration coefficient of a dialyzer, QUF or ultrafiltration rate, and the transmembrane pressure in millimeter mercury. The magnitude of the filtration in hemodialysis is determined by hydraulic permeability of a dialyzer, surface area of the membrane and the piezometry of the dialyzer. Narrower fiber has more ultrafiltration capacity, as well the hydrostatic and oncotic forces acting on the blood, which limits the ultrafiltration. So increased hydraulic permeability, as well increasing the surface area of the membrane, increase ultrafiltration, while increased hematocrit and protein content of the blood limit the ultrafiltration. The phenomena of back filtration means a situation where there is a transport of fluid from the dialysis fluid side into the blood side, and this is phenomena encountered with high flux dialysis and is due to excessive ultrafiltration through the first half of the dialyzer that follow a pressure drop on the second distal part of the dialyzer, and so pressure moves the fluid from the dialysate side into the blood side. In low flux dialysis, the dialyzer has very limited KOF, so need more transmembrane pressure, so no back filtration. while in hemodiafiltration, you need to remove excess fluid, so need higher transmembrane pressure all through the dialyzer length and subsequently no back filtration. Only on high flux, back filtration occurs due to obligatory fluid loss and the pressure drop. In the middle of the dialyzer, there is a filtration equilibrium point where filtration happens in the first part from the blood side towards the dialysate side, subsequently a pressure drop. Higher pressure in the dialysate makes the back filtration. In hemodiafiltration, no back filtration due to high transmembrane pressure all through the length of the hemofilter. So water moves almost from the whole length of the dialyzer.